A common component in drive technology is a solenoid, and that's because a solenoid is a cheap and simple actuator. But on the other hand, its behavior is very nonlinear, making modeling difficult. My name is Stef Winterake, and in this video I'm going to talk to you about the operation and modeling of a solenoid. First, let's look to the structure of the solenoid. Here we have the fixed part, which we also call the housing, and it's made of iron or low carbon steel. And on the inside of the housing there is a copper winding, that is a coil, which is not visible of course in this picture. And this winding is carried out through the red and black wires over here to the outside world, and in that case we can apply a voltage to that solenoid. And if we do that, then a current goes through the coil, so we have created an electromagnet. And a magnet attracts iron, so the movable part of the body over here, which we call the plunger, is made of iron and or low carbon steel as well. And attached to the plunger there is a mechanism which we want to move, of course. So when I put a voltage on the connecting wires of the solenoid, the plunger is pulled in and the mechanism moves. And to get the mechanism back to its original position when the voltage is disconnected from the solenoid, there's a spring attached over here. And that pushes the plunger back to the original position when the solenoid is unpowered. So now let's see what physical laws play a role in the operation of that solenoid. Suppose I have a wire through which a current flows, like here. Then a magnetic field is created and the field lines are created around these wires, denoted by the letter B. The greater the current, the greater the number of field lines, so the greater the total magnetic field. Now if this wire is in a way that a coil is formed, so like this, and I connect a current source to that coil, then a magnetic field is concentrated according to the purple dotted line, so like this. So we have a magnetic field concentrated like these, according to these magnetic field lines. And in this way an electric magnet is created with the North Pole and the South Pole. As a result of that magnetic field, a flux is created, and that flux is equal times the magnetic field strength, B, times the surface area A of the coil. So it's B times the area A over here. The symbol of a coil is shown over here. So this is a symbol of an electric coil. And that coil is characterized by the self-inductance L. And that self-inductance is equal to mu, and mu is the magnetic permeability, times the number of windings squared, so times n squared, times the area A of the coil, divided by the length of the coil, the length over here. And that magnetic permeability, that mu, depends on the material through which the magnetic field lines flow. So it's equal to the degree to which the material conducts magnetic field lines. Because the magnetic permeability of iron, for example, is greater than that of air, the house of the solenoid is often made of iron, and the flux is also equal to the self-inductance L times the current through the coil. So it's L times I, or L times IR in this case. And when a current flows through the coil, it creates a voltage across the coil, which is equal times the derivative of the flux towards time. Well, these are the basic equations for modeling an inductor. So now let's look to the equivalent circuit of a solenoid. And let's start with the equivalent circuit of the electrical part of the solenoid. Well, here we have that solenoid again. This is the housing, and in this housing the coil is situated over here. And you can see it over here, but it's of course not visible because we have a picture which doesn't show that. And we have the plunger over here made of iron, and when we connect the windings, so the coil over here, when we connect these windings to a power supply, then a current will start to flow, which generates a magnetic field, and the magnetic field and the flux will cause a force acting on that plunger, and it starts to move. And the maximal stroke the plunger can make is the stroke over here. So after that position, the plunger is at its maximal inner position. And also connected to that plunger, there is that spring which we discussed over here. So now let's look to the equivalent circuit of a solenoid, and we have to make a model of these windings over here. And these windings can be modeled as a series connections of a coil and a resistance. So we have a coil over here, which is L, and a series connection of resistance over here, the resistance of the copper wires of these windings. And what we have seen is that inductance value is not a constant value because it depends on that mu factor, that magnetic permeability. And we've seen that the magnetic permeability of iron is higher than that of air. So when the plunger starts to move, then the flux, more flux is flowing through the iron part, so less of the flux is flowing through air. So the inductance value changes whenever this plunger moves. But there is a second aspect which takes place when that plunger moves, and that is that it creates a back EMF voltage, UEMF. So when the plunger moves, it also creates a back EMF voltage, which is a series connections is in series with that R and that L. So again, when we add a voltage through that solenoid, a current flows through these windings, which can be modeled as a series connection of an R, an L, which is not constant, and a back EMF voltage. And keep in mind that when the plunger is at its maximum inner position, of course, then the plunger stops to move, so also in that case the back EMF voltage is again 0. That brings us to a situation in which we can look to a important diagram of a solenoid, which is the current diagram. And this is a current diagram of a solenoid, in which we have the time on the horizontal axis and the current on the vertical axis. And in this figure we have divided this figure into 5 more or less pieces, 1 to 5. So what happens in area 1? Well, in area 1 the current starts to increase, but the current value is too low to create a force on the plunger. So in that case the plunger doesn't move, so the back EMF voltage is 0. But the shape of the current is an e-power shape, and that is because we have an L and an R in series, which creates a time constant, which is L over R for a series connection of an R, a resistance, and an inductance value L, and the shape is an e-power shape. So that is what happens in area number 1. And in area number 2, the force created by the current is high enough to get that plunger to move. So in that case, 2 aspects are created. The first aspect is that the L starts to change. It will become higher because the flux is more flowing through the iron, so the permeability of iron was higher, and L was depending on the magnetic permeability, so L starts to increase. So the time constant L over R starts also to increase. But also the back EMF is created because due to the movement of the plunger, that back EMF voltage is created, which was in series with the R and the L. In part 3 of the curve, the back EMF voltage is at such a high value that the derivative of the current becomes negative. So we get that shape of the current diagram over here. And at this point, in part number 4, then the plunger is at its maximum position. So at that point over here, suddenly the back EMF voltage is 0, and the inductance value is at its highest value. So the back EMF voltage is suddenly 0. So my current still keeps on increasing with an e power graph, so to say, and the L is at its maximum value, so the time constant L over R is still a high value. So it keeps on increasing up to its maximum constant value, which is equal to the applied voltage UB over the solenoid resistance value R. So that is the basic current diagram of a solenoid. So when you, for instance, measure that current through a inductive probe and an oscilloscope, and when you measure this point in time, you know exactly at which point in time the plunger is at its maximum inner position. All right. Now let's look to a number of equations which are necessary to get a model of that solenoid. So first of all, we start with the voltage equation for the solenoid. And that voltage equation says that the voltage, the applied voltage UB, is equal to R times I, so R is the R solenoid value over here, plus the derivative of the flux towards time. And we've seen that the flux is equal to L times I, so we can say the applied voltage is equal to R times I plus the derivative of L times I towards time. But keep in mind that that L value, that inductance value, is not a constant value, so we may not put that in front of the derivative over here. So we have to change that formula, and this way we have to say, well, the voltage is equal to R times I plus L times the I dt plus I times the L dt, because this is not a constant value again. So this is what we called the back EMF voltage, so we can also say that the voltage is equal to R times I plus L times the I dt plus the back EMF voltage U EMF. This EMF voltage, we can also put that in another way, because the derivative of the inductance value towards time can also be written as a derivative of the inductance towards the position of the plunger, which is often more of interest. And when we do that, so when we change dl dt in dl over ds, we have to correct it with ds over dt, so then we get the same expression back over here. And ds dt, the derivative of the position of the plunger towards time, is of course the speed of the plunger. So in that case we can write the back EMF voltage as the current I times the derivative of the inductance value towards position of the plunger times the speed of the plunger. So that is an expression of the back EMF voltage in this voltage equation over here. So that is my voltage equation. Then we can discuss two important diagrams, and the most important diagram, of one of the most important diagrams, is the force stroke diagrams. And often a solenoid supplier, when you have a good supplier, he mentions this graph in his data sheet. And on the horizontal axis of that graph we have the stroke in millimeters, and on the vertical axis we have the force over here. And you see that there are a couple of characteristics you can have, like the red one or the blue one, or even the black one is sometimes a force stroke curve, which you can see or can get from a solenoid, and it all depends on the construction of the solenoid and of the plunger. Keep in mind that when you increase the current through the solenoid, also the force increases. So in that way that curve increases, not to an infinite value, because when saturation takes place, then there is no more force coming out of that solenoid when you increase the current. So that is an important diagram, the force stroke diagram. And then we also have an induction stroke diagram, often in a data sheet, which is another way of putting that dl/ds, so the derivative of that inductance value, towards the position of the plunger. it's also often put in a diagram or in a table, and that data you can use for modeling that solenoid. So now we have modeled the electrical part of the solenoid. We want to use two diagrams, the relation between the force and the stroke and the inductance of a stroke within our model. And of course we have to add the load to the solenoid and also keep that in our model to get the complete modeling of our system. And in this situation we have an example of a solenoid which is mounted in this position, in a vertical position. And of course you can also have a horizontal position or even other position, but we take this as an example in which we have the solenoid over here. This is the housing, and in the housing we have the plunger over here. This is my maximum stroke, S, and towards that plunger we have our load added, and in this situation the load is added directly to the plunger. But if there is a transmission between the plunger and the load, then the equivalent load mass is equal to the load mass times the transmission ratio squared. So keep that in mind. So when we add the load to the solenoid, we also have to add the mechanical equations to our model. So we have to define the equations of motion. So first of all, let's define a couple of things. Well, when we activate the solenoid, there will be a plunger force in the vertical direction, so it will move in the downwards direction. So the position of the solenoid is in that direction, and the position of the solenoid is depicted by that letter X over here. Also, often you see a damper in a solenoid, the damper D over here, which is in many situations added to minimize the audible noise when the plunger hits the end stop over here, so to get rid of that click noise when the plunger adds that maximum or the maximum in a situation, so when the stroke becomes 0. So to reduce that value. So when that plunger is, when the damper is also added to your solenoid, you have to take that into account in your equations of motion. So first of all, let's define a couple of forces acting on my plunger in this example. So first of all, we have, of course, the solenoid force, which is acting in that direction when we apply a voltage to that solenoid and that current starts to increase. Then, of course, we have the gravitation force acting on that plunger over here, which is M times G. And of course we have also the gravitation force acting on the load mass over here, or on the equivalent load mass when there was a transmission between the plunger and the load. So all these three forces are acting in a downwards position. We have also three forces acting in the upper position, which is, of course, first of all, the friction force, especially at this point where the plunger is moving in and out of the housing. So that plunger force is acting in the opposite direction than the solenoid force, so in the upper position. We have, of course, the spring force caused by that spring over here, and when we have a damper force, we also have a damper force acting in the opposite direction, so in the upper direction over here. Well, now let's add all the equations which are necessary when you want to define a model, either in Excel or in MATLAB, or using Simulink, for instance, which is a really nice environment for making a model. So we had the electrical equation, which said that the voltage was equal to R times I plus L times di dt plus the back EMF voltage I times dL ds times the speed of the plunger over here. And keep in mind, of course, that when the plunger is at the maximum inner position, this voltage should be becoming instantly 0. So you have to keep that in mind, that you put that instantly to 0, because the plunger isn't moving in that situation, that maximum inner situation. Well, this was the electrical equation. Then we have the relationship, of course, between the current and the force, which is often a graph in your data sheet. And then we can define the equations of motion, which says that the solenoid force plus the gravity force on the plunger plus the load force on the plunger minus the forces in the opposite direction, the friction force, the spring force, and the damping force, equal, according to Newton's law, the sum of the load mass plus the plunger mass times the acceleration of both masses. And the acceleration is, of course, a double derivative of the position. And, of course, keep in mind that a damping force is equal to the damping constant d of that damper when it's in your solenoid application times the speed times the derivative of the position, and the spring force is, of course, spring constant k in my example times the position x over here. So these are all the equations you need for creating a model. And there is one more thing which I want to discuss with you, and that is the temperature effect, which could be applicable when you use a solenoid in a application in which you activate that solenoid for a long time. Let's say for 3 to 5 times or even more times the time constant of that solenoid. In that case, a couple of things change, because heating up of that solenoid, the R will change, so the maximum current will change, it will be lower, so also the force generated by the solenoid will be lower. But also to the changing R, the point in time in which the plunger acts its maximum in a position will be at a different point of time. It's in most of the situation it's at a later point in time, so also the dynamic aspects of that solenoid change. So when you want to take the thermal effects into account, which you should do when you have a more or less static application, or application in which you put on the power to the solenoid for a long time, let's say 5 times time constant, thermal time constant of that solenoid, you should take into account that first of all, the R is depending on the delta T of the solenoid, and you can calculate that actual R, that actual resistance value, by multiplying the resistance value, for instance, at 25 degrees times 1 plus the alpha, which is the temperature coefficient of copper, times the delta T. So times the temperature increase of the solenoid. And the temperature increase of that solenoid is equal to the dissipation power times the thermal resistance between the windings and the ambient. And also this value, you find it often in the datasheet when you have a good solenoid. And the last equation we have to use is the definition of the dissipation power, which is the RMS voltage squared divided by that R over here. So again, when you want to take the temperature effect into account in your model, then you have to apply these equations. Well, that's all about modeling a solenoid. I hope you enjoyed the video. Good luck with your model. Bye-bye.